All right, and we're back. So, take a look at this guy. It seems to be exactly what we've already done, right? Seems to be exactly what we've already done. We have to take one thing into account with this one. We've got these two masses on here. Um, they have a moment that's applied, and it tells us that there is also a force that's been applied. Okay, to each sphere 10 newtons. Okay, so that is going to create another moment. So really, we need to deal with two moments when we're taking this into account. So we call it M1, M2, and M3 as we get into this thing. So M1, I will call just that applied moment, which is 8t. All right, then there's M2, which I'm going to call P times R. And P is the force 10 newtons, and then R is 0.5. And of course, we've got M3, which is also a PR. And they happen to be working in tandem, they're working together with each other. So our total moment is PR plus PR. And then the shaft, which is providing 8T. So we end up with a total moment, which is going to be 8T plus 2PR. All right. Then all we have to do is, this story is getting kind of boring at this point, but we're going to look for our delta H, and that's going to be the integral of m dt. And we're going for 4 seconds. So we go from 0 to 4. And we started at rest, which is nice because that means our initial angular momentum is also 0. And the delta H, if we get to working on that, then we're dealing with 8t plus 2pr dt. All right. So let's carry that out just a little bit further here. I'm going to go this way with that. So we got 4t squared plus 2prt integrated from 0 to 4 seconds, just like that. So if we plug in our 4, we got 4 times 4 squared, which is 16. So that is 64. So we've got 64 plus 2pr times t, which is 4. All right. Giving us 64 plus 8pr. If we substitute in for what P and R are, P is 10, R is a half, so P times R is 5. So 64 plus 8 times 10 times a half. Okay, that's 5 times 8 is 40, so that's 104 is our change in angular momentum. Okay, now the only thing that's has the potential to get wonky on this is once you go to that next step. Because in that next step, what we're going to want to say is that HF is HI plus our delta H. Okay, and our HI is 0 on this thing. So let me scoot over to the other side here. So we find that our final is our delta, which is that 104 number, just like that. But what do we put for? What do we do with that? Okay. In this case, we've got these two objects. All right. So we've got M1 R1 V1 plus M2 R2 V2. That's equal to 104. Fortunately, the r's are the same, the m's are the same, and the velocities will be the same too. Okay. Now, if for some reason the velocities weren't the same, then we'd have some kind of weird thing where one of the balls could catch up with the other one, something like that. Okay. And they're rigidly attached, so we don't expect that at all. Okay. Now, if the R values weren't the same, then it could be one is going slower than the other one. And we might have some kind of strange situation where one ball is moving like this on the inside and the other ball is moving further out on the outside. So then we have to figure out, well, how does it mean, or how do we find what the velocity is? But fortunately, we're not in that position. And so we can reduce our equation that we have just to 2m1 r1 v1 is 104. All right. Plug in the mass, plug in the radius, solve for the velocity. Just that straightforward.